In classical mechanics, today we are going to start a new chapter which is very conceptual, very useful, and very thoughtful. And this is the concept of small oscillations. In fact, you have studied this small oscillations in your lower classes, but in this lecture series on small oscillations, we will see the advanced concept of small oscillations. In fact, you know that this problem of small oscillations, when you say small oscillation, that means oscillation or vibration with a small amplitude. This is just a key problem of physics. Why this problem of a small oscillation is called key problem of physics? Because you know that the theory of small oscillations finds its applications in various branches of physics. And definitely you have been encountered with this problem while studying the different branches of physics. As for example, you can say that when you study the molecular spectra, then we study their rotational vibrational spectra, and the concept of linear harmonic oscillator is in fact used there. Okay. Similarly, in acoustics, we find the problems on small oscillations. In solid state physics, while studying the vibration of atoms in solid, you face this problem. And in case of electrical circuit, you study the LC oscillation. Okay. In quantum mechanics, this is a very important problem. While studying the quantum dynamics and the problem of linear harmonic oscillator, you in matrix formulation of quantum mechanics and several other places, you find the problem of a small oscillation. And most importantly, in classical physics, you have been studied the problem of a spring mass system, simple pendulum, bar pendulum, compound pendulum, Ketter's pendulum, and so on. And everywhere you have faced this problem of small oscillations. So this problem of small oscillation is very important, and its concept is somewhat you can say its concept is somewhat tedious. But when you will watch my videos on this of this chapter, the advanced concept of oscillations will be definitely clear to you. Okay. In fact, in classical mechanics, it is not a new concept for you, because while studying the Lagrangian formulation of quantum mechanics and the Hamiltonian formulation of quantum mechanics, you have studied such problems too. In fact, in Lagrangian formulation, the harmonic oscillator problem was dealt for those harmonic oscillators which had only 1 degree of freedom. Okay. But in this chapter, we are going to generalize that problem. It means we have to generalize the problem in such a way that the degree of freedom will be not limited to 1, but we will see the oscillation of such a system which has actually several degrees of freedom near the equilibrium position. Okay. And so this, you can say that we are going to discuss the theory of small oscillations in general form, where we will deal with the harmonic oscillator problem, not of only 1 degree of freedom, but several degrees of freedom. Okay. And that's why we will get some new idea, new concept, new results. Okay. In fact, when we will study this chapter, you will see that we will solve the problem of coupled oscillators. While studying the problem of coupled oscillators, you will see there will be some very interesting and surprising result. Okay, when we will solve such problem, you will get that there are very interesting and surprising results. Okay, if you consider that there is a system of n coupled oscillators with n degrees of freedom, then you will find that there will be exactly n independent modes of vibration, or you can say n independent normal modes of vibration. Okay, and the general motion will be just the superposition of n normal modes. Okay, in fact, when you will consider a system consisting of a very large number of particles, exceedingly large, or you can say infinitely large number of particles, such that the interparticle separation or interparticle distance is almost equal to 0, then such a medium is treated just like a continuous medium. And in fact, in that condition, while discussing the oscillation, we will discuss it just in terms of waves. So the idea of waves is also developed from the idea of vibration. In fact, in that condition, our system in our system, the particles are distributed just in a continuous fashion, in a continuous manner, and then that vibration can be described in terms of waves. Okay. Now, any oscillator vibrate or oscillate about equilibrium position. So before starting this very chapter, I would like to explain the concept of equilibrium. So in this introductory lecture, or the first lecture on a small oscillation, I am just going to explain what is equilibrium and what is why we are going to study equilibrium, because I have told you that the oscillation always takes place about the position of equilibrium. So definitely the concept of equilibrium must be in your mind to understand the concept of oscillation. Okay. This equilibrium is also not new for you, because you have definitely studied the concept of equilibrium in your lower classes. So this is just a revision, so that you will not find any difficulty in understanding the concept of a small oscillation. In fact, when you say that there is a system which is in equilibrium, what does it mean? A system in equilibrium means that the net force or the resultant force on the system is 0. In other words, we can say that if a resultant force on a system is 0, then such a state of the system is called its equilibrium state. Okay? Net force must be 0 on the system to be in equilibrium state. Okay? So, in fact, this concept of equilibrium can be understood in terms of potential energy, because you know, in the advanced classical mechanics, where we talk about the Hamiltonian mechanics and Lagrangian mechanics, we do not talk in terms of force, but we always talk in terms of energy. So the concept of equilibrium should be also in terms of energy. In fact, for a conservative system, the concept of equilibrium can be described in terms of potential energy of the system. You know that a conservative system is always associated with a potential energy corresponding to the conservative forces. Okay. So, to understand the idea of equilibrium, let us consider a conservative system, and this conservative system has, let us say, degree of freedom f. F is the number of degree of freedom of our conservative system. And as you know, if f is the number of degree of freedom, definitely the number of independent variables or the number of generalized coordinates to specify the configuration of the system must be equal to f. And we denote those generalized coordinates by the symbol q1, q2, q3, so on qf. So you can say that these q1, q2, so on qf are the generalized coordinates of this conservative system. Okay. In brief, you can also say that the generalized coordinate of this conservative system are qk, where k is 1, 2, 3 and so on up to f. Okay. And we also assume that the time variable does not occur or does not involve explicitly in describing the state of the system. It means you are considering the stationary system, time independent. Okay. In fact, if the potential energy of such a system can be expressed, definitely that potential energy as depends on the configuration of the system, and the configuration of the system is described in terms of the generalized coordinates. So you can definitely say that the potential energy of such a conservative system will be just a function of these generalized coordinates. Okay. So you can write that the potential energy function of this conservative system is just equal to V of Q1, Q2, so on Qf. Okay. And as you know that the generalized forces are simply the negative of the partial derivative of potential energy function with respect to the generalized coordinate. Or in other words, we say that the generalized force is the negative gradient of the potential energy function. So if you write the kth component of the generalized force by the symbol gk, this gk represents the kth component of generalized forces, then gk is equal to minus del v by del qk. You know it. In the very beginning of Lagrangian formulation, we have defined the several generalized quantities, and there you will find in my video the concept of generalized force, and that generalized force is defined like minus del v by del qk. Okay. Now, as in the beginning I have told you that any system is said to be in equilibrium when the net force on it is equal to 0. So if net force will be 0, each and every component of the force will be 0. If net force is 0, then each and every component of the force will be 0. For example, let us consider the not generalized force, but in general the force vector. And you say that this force vector is 0. And in the 3D space, you write this force vector as fxi plus fyj plus fzk. You write it. And this is equal to 0. You know, if fxi plus fyj plus fzk is 0, it is possible only when all these components are separately equal to 0. Only then this force will be 0. So if our system is in equilibrium, then in accordance with the definition of equilibrium, we can say that the kth component of the generalized force gk will be equal to 0. It means g1, g2, g3 all will be equal to 0. Okay. But as we know that this gk is equal to minus del v by del qk, and at the equilibrium position this should be equal to 0. So we can say that minus del v by del qk is equal to 0 at the equilibrium position. Here this subscript 0 actually refers the equilibrium position. Okay. This subscript which I have mentioned here outside of the bracket, that actually represents what? That represents that we are talking about the value of this minus del v by del qk at the equilibrium position. And at the equilibrium position, this will be equal to 0. Okay. Now, since in RHS there is 0, so you can omit this minus sign and simply say that this del v by del qk at the equilibrium position is equal to 0. So this is the condition for equilibrium in terms of potential energy function. So whenever we have to test that any position or any configuration or any state of the system is a equilibrium state or not, what we will check? We will simply find the partial derivative of this potential function with respect to the generalized coordinate at that very position, and if that will be equal to 0, you can say that the system is in equilibrium. Okay, this is the mathematical condition for equilibrium in terms of potential energy function. But you know that if del V by del Qk at the equilibrium position is 0, what does it mean? It means at the equilibrium position, the potential energy function will be extremum. Potential energy function of the system will be extremum. When you say extremum, what does it mean? It means V is either minimum or maximum or stationary. When you say stationary, that means constant. It means at the position of equilibrium or in the state of equilibrium, the system has either minimum potential energy or maximum potential energy or constant potential energy. Constant potential energy means when you will change the state of the system slightly or position of the system slightly, there will be no change in potential energy. So in these three conditions, the system will be said to be in equilibrium. So for equilibrium, what is the condition? Condition is potential energy function of the system must be extremum. When you say extremum, extremum word means either minimum or maximum or stationary. Stationary means constant. Okay, and this is actually also if you plot a graph, let us say between these generalized coordinate, particular value of generalized coordinate Qk and V, and let us say that this is our curve. Then del V by del Qk means what? At any position, del V by del Qk represents the slope of that point, slope of the curve at that point. So you can also say that if the slope of the V versus Qk curve, V versus Qk curve, which is actually called potential energy curve, is equal to 0, at that point the system is in equilibrium. You can say if the slope of the potential energy curve is 0 at a particular point or in a particular state, then the system in that state is called equilibrium state, or you can say that state of the system is the equilibrium state. Okay, so you can see I have actually mentioned this fact here, that if the system is in equilibrium, then potential energy of system is extremum, that is either minimum or maximum or stationary. Now let us see that this position, let us say O, is the equilibrium position of our system. So if the initial velocity of our system is 0, then if the system will be at the equilibrium position, it will be permanently at that point. It will be never displaced. Okay. So at the equilibrium position, the system remains indefinitely for long time, for all time, if the initial velocity of the system is 0. Or if we do not displace the system or do not disturb the system, then the system will permanently remain at the equilibrium position. Okay, so I hope you have understand what is the idea of equilibrium in terms of the potential energy function. The main thing is only two. First of all, you can say that the state of a system when net force on the system is 0, that state is called equilibrium state. And if net force is 0, then the negative of the gradient of the potential energy function should be 0. And that means the potential energy function of the system must be extremum if the system is in equilibrium. And extremum means the potential energy function will be either minimum or maximum or constant or stationary. Okay. Now actually this equilibrium is of three types. The first one is known as a stable equilibrium. The second one is called unstable equilibrium, and the last and third is called neutral equilibrium. Now we will understand what is this stable, unstable and neutral equilibrium separately. Okay. This is a very simple concept, you can easily understand it. So let us first of all see the idea of the stable equilibrium. In fact, for getting the idea of a stable equilibrium, let us consider that see this figure 2. This is just a vessel of concave shape, just like in Hindi you can say a katora. Okay, and at the lowest point of this vessel, let us consider there is a system or there is a particle which I have shown by this small sphere. You can say by your experience that if this particle is at this lowest position and you watch the system at different times, you will find that this system or this particle remains at that position A permanently. Okay. Now let us consider that this particle is slightly displaced to this position P from this position A and released. When the particle will be displaced from position A to P and released, then what will happen? You can say actually this particle will back and reach to this point A. But as you know, the particle has mass, so due to inertia it will shoot out in another direction and reach to the point Q. And when it will move from A to Q, its velocity will get decreased, and at reaching this point Q, its velocity will be again 0, and then it will again back to the position A. So in this way you can see that our particle will in fact make motion about this point A, and whenever you will displace this particle from this position A aside, slightly aside, then there will be a bonded motion, not unbounded. This type of motion is called a bonded motion. It means the part I have shown in this figure, the particle is displaced to the position P and released, then it will come back and go in the another direction and again come back to A, and again it will move towards P. And so in this way, if a slight displacement is made from the position A, then the particle will perform a bonded motion. In fact, if a particle performs a bonded motion about a particular point, that very point is actually the stable equilibrium position of the system. So you can say that this position A in figure 2 is the stable equilibrium position. Okay. I have mentioned this fact here. You can see that a system is said to be in a stable equilibrium if a small displacement of the system from the rest position results in a small bonded motion about the equilibrium position. Okay. Now, we can understand this concept of a stable equilibrium from this figure 1, where I have actually plotted the potential energy function V of the system in against of a particular value of generalized coordinate qk. So this is just a graph of potential energy function and the generalized coordinate qk. Let us see here. This is V versus qk graph. Okay. Actually, this graph which has been plotted between V and qk is called potential energy curve. And I have assumed it here. We are not given any potential energy function related to this qk, but let us say that if V is plotted in against of qk, we get a curve like this, which I have shown in this figure, and I am just marking this path, you can see. Okay. Now, this is just a potential energy curve, and if you see this figure, then you can find that corresponding to point A, the potential energy function of this system is V naught, and at any other point the potential energy is greater. It is greater than V naught. So you can say that potential energy function at point A, corresponding to point A, is minimum. Okay, and you have the point corresponding to which the potential energy function is minimum. At that point the value of qk is q naught. Okay, in fact at this point, when the system will be at this point, its potential energy will be minimum, and this equilibrium minimum, and this equilibrium position is called a stable equilibrium. This is called a stable equilibrium because whenever the particle will be displaced from this position, definitely its potential energy will increase and the kinetic energy will decrease. Okay, and if you let us take this particle at this position q, and its total energy is equal to E here, then E minus V naught, this much energy has been converted into the this is actually the increase in potential energy. Okay, E minus V naught is the increase in potential energy. Now you can see, corresponding to this point, if you want to find the slope of this potential energy curve, how we find the slope? For getting the slope of this curve corresponding to point A, we have to draw a tangent. And you can see the figure, this tangent will be just parallel to the qk axis. So if tangent is parallel to the qk axis, it means the slope of this curve corresponding to point A, which is equal to del V by del qk at q equal to q naught, this will be equal to 0 because it makes angle 0 with qk, and slope is equal to tan psi, where psi is the angle made by this tangent to the qk axis, and this is actually 0, and tan psi and psi is 0, so this will be equal to 0. So slope is 0. And it is also found that when we will take the second order partial derivative, that is del 2v by del qk square, del 2v by del qk square, then this will be actually positive because a small displacement from this position A increases the value of potential energy, and so this second order derivative will be positive. I have mentioned it here. You can see that at corresponding to point A, slope of the curve is equal to 0, and the second order derivative is greater than 0. And if second order derivative is greater than 0, that means what? You have definitely studied the condition of maxima and minima. In this condition, you can say that V is minimum at corresponding to point A. And this actually corresponds to the stable equilibrium. So you can say that if the potential energy function of a system is minimum at the equilibrium position, then we say that such a equilibrium position is a stable equilibrium. At a stable equilibrium position, the potential energy is minimum. Okay, so I hope you have understand the idea of a stable equilibrium. Now we will see the idea of unstable equilibrium. This is just reverse of that. For getting the idea of unstable equilibrium, let us now invert that katura, invert that pot, which is now in fact of convex shape. So this is just a convex surface, you can say, and let us put a particle or a body or a system at its top position. It will remain in equilibrium, it will be stationary. But imagine from your experience that if this particle will be displaced to this position and released, what will happen? This particle, when displaced from this position B, will not return back to B, but it will move away from B. And if you will displace this particle to this position, let us say C, then it again moves away from position B and never returns back to position A. This is called unbounded motion. So we simply say that a system is said to be in unstable equilibrium when the system is displaced from its equilibrium position slightly and the system performs unbounded motion, not bounded motion about that point, then this equilibrium position is called unstable. Okay? Equilibrium position is called unstable. Okay? Now, the same fact we will understand on the basis of this potential energy curve. Here again in this figure you can see we have shown a plot of potential energy function V in against of a particular value of the generalized coordinate qk. Okay? And if the potential energy curve is like this shape, which actually have shown in this figure, then you can see that corresponding to this point B, the potential energy function is maximum, which I have denoted by the symbol V naught. Okay? And corresponding to this point, if you will want to find the slope of the curve, this will be again 0. For getting the slope, what we will do? We will simply draw a tangent at this point B, and you can see that I have drawn here a tangent, and this tangent is parallel to the qk axis. Okay? And so the slope tan psi will be again 0, because psi is the angle made by this tangent with qk axis, but it is parallel, so psi is 0 and tan psi is 0. And tan psi, according to calculus, this will be del V by del qk when qk is equal to q naught. See here, corresponding to this point P, the value of qk is q naught, and this is equal to 0. And at the same time, you can see when you will find the second order derivative, that is del 2V by del qk square, when q is equal to q naught, then it is found that this will be less than 0, that is negative. And if it is negative, according to calculus, according to the condition of maxima, this potential energy function will be maximum. So this point B corresponds to the maximum potential energy of this function. And this also corresponds to the unstable equilibrium. So in one sentence, you can say that the state of the system when its potential energy function is maximum, that is called unstable equilibrium state. Okay? When V is maximum, that is called unstable equilibrium state. When V was minimum, that was a stable equilibrium state. And when V is maximum, that is unstable equilibrium state. And all these things which I have just explained, that are here mentioned for your convenience. You can note down these things in your notebook. You can see that I have mentioned that a system is said to be in unstable equilibrium if a small displacement of the system from the equilibrium position results in an unbounded motion. Mark it, unbounded motion. And according to the V versus K graph, it is evident that the corresponding to the point B, that is qk equal to q naught, del V by del qk at q naught is 0 and del 2V del qk square at q naught is less than 0. And if it is less than 0, V will be V max, which I have assumed V naught at this position Q naught. And so this implies that Qk equal to Q naught. This is the unstable equilibrium position of our system. Okay. So I hope you have understand the concept of this unstable equilibrium. Okay. Now the third one, which is called neutral equilibrium. For getting the idea of neutral equilibrium, let us consider now there is a plane surface. You can see this is a plane surface. Okay, just like surface of your table. And at that plane surface at any point C, let us consider there is a small sphere or any particle or any system placed. Now let us displace this particle from this position C. At C, the particle is at rest, it is in equilibrium, and we simply provide a small displacement to this particle on this horizontal or this plane surface. Let us say it is displaced to the position D. What will happen? You can easily say from your experience that if the surface is horizontal, it is plane, then after displacing the system from this equilibrium position C to D, again this particle will remain in equilibrium. It will neither move towards C nor away from C. It means this particle will neither perform a bounded motion nor an unbounded motion. It will perform no motion. Similarly, if you displace the particle at this position E, even then you find that the particle will again remain at rest. So you can say that if a system is in a neutral equilibrium, what will happen? Then after providing a small displacement from the equilibrium position, then the particle will not execute any type of motion. The particle will be again in equilibrium position. Okay. So this is so in this condition you can say that this point C or D or E all are actually the position of neutral equilibrium. Okay. In fact, I have mentioned it here. You can see that a system is said to be in neutral equilibrium if the system on displacement has no tendency to move about or away the equilibrium position. Okay. So such an equilibrium position is called neutral equilibrium position. Now see this figure 5 where I have plotted the potential energy function in against of Qk, that is generalized coordinate. In fact, if the system is in neutral equilibrium, its potential energy function is completely independent of position. You can see here the potential energy of the system at point C and at point D, at point E, everywhere is same. So the potential energy function does not change with change in position. Okay. So you can say that if the system is in neutral equilibrium, its potential energy will be independent of generalized coordinate or independent of position. So when Qk is 0, then V is equal to V naught. When Qk is, let us say this much, again you can see that V is equal to V naught. When Qk is equal to, let us say this much, let us say Qk is here, Q1, here, there it is Q2. For all values of Qk, you see that V does not change, it remains constant, and so this curve is just parallel to Qk. Okay, just parallel to Qk. And since it is parallel to Qk, so the slope at any point on this curve will be equal to 0. Okay, del V by del Qk at any Qk will be equal to 0. And in that condition, we say that our system is in neutral equilibrium. So main fact is that in neutral equilibrium, potential energy function is stationary, it is constant, it is independent of position. Even after a displacement from the equilibrium position, potential energy function does not change. So I have mentioned it here. You can say that in this case, the potential energy is independent of the coordinate and equilibrium occurs at any arbitrary value of the coordinate. So V equal to V naught for all qk's and del V by del qk equal to 0 for all qk's. Okay. And so you can say that V is a stationary. A stationary means constant, and this represents actually the neutral equilibrium. Okay. So these three types of equilibrium, I hope you have understand. But what you think when you talk about the oscillation or vibration of a system, about an equilibrium position, about which equilibrium position vibration will take place? Can you say? Definitely, you have seen that in case of a stable equilibrium, the particle performs a bounded motion about the equilibrium position. So definitely, when we talk about the oscillatory motion or vibratory motion, that motion always takes place about the stable equilibrium position. Vibration will not take place about the neutral equilibrium position. Vibration will not take place about the unstable equilibrium position. It will always take place about the stable equilibrium position. So a stable equilibrium position regarding this oscillatory motion is the most important, because oscillation always takes place about the stable equilibrium position. So this was just an introduction to this chapter of a small oscillation, and after this introductory lecture, in the forthcoming lecture we will start the real concept which we have to discuss. Actually, as I have told you that the name a small oscillation of this chapter does not mean that we will study simple harmonic motion which we have studied in your class 11th or in the Lagrangian formulation. But I will provide you just a advanced course in the chapter a small oscillation, which actually covers the syllabus of MSc semester 1 of several universities and the BSc part 3 honors of physics of several universities. Okay. Thank you very much.